All right, let's tackle number 3. Johanna, not Joanna, Johanna jogs along a straight path for 0 to 40. Johanna's velocity is given by this differentiable function, v, given in the table. Selected values v are measured in meters per minute, are given in the table above. Okay, so let's talk about what we know so far before we ever read any further into the problem. She's jogging along a straight path, and I'm just saying this because that negative right there is throwing me off, but it's not, right? Because this is jogging away, jogging back toward wherever she was, jogging away, okay? When they give us our velocity, they better give us a rate, excuse me, and they did, meters per minute. So meters and minutes are going to come up in our problem a lot as units if necessary. And we'll just go ahead and jump right in with part A. Use the data in the table to estimate the value of v prime of 16. So here's number 3, part A. Excuse me. Well, since this is an estimate, I'm not going to put equals, I'm going to put approximately. And if I want to know the slope at 16, don't make it harder than it is, right? Where is 16? Well, it's in between 12 and 20, right? So 16 is around here somewhere. So if I want a 16, it's here, then I better find the slope between 12 and 20. So 240 minus 200 over 20 minus 12, and that's going to give me 40 over 8, which is 5. Now, okay, I'm done, but I'm not done. Let's go a little bit further, and let's go ahead and call it what it is. This is the derivative of velocity, which is acceleration. So meters per minute. So meters per minute squared. And in case you want to know how they grade it, you got a point right there. You didn't necessarily get a point for the meters per minute squared, but it's good to know, right? All right, let's move on to part B. Part B, I'm going to go ahead and confess a mistake that I made when I was doing this problem. There are a couple mistakes, actually, when I got to part B. And my first mistake was this. When I was doing this, I read it, did the first part, and didn't answer the second part. So sometimes, even within a part like part B, you'll have two different things. So using correct units, explain the meaning of that in the context of the problem. I did that, and then I moved on to part C and realized, wait a minute, I haven't done that part yet. Made a separate mistake in this one. I'll tell you what it was when I get there. So I'm going to just go ahead and start writing down a sentence. And that sentence is going to start with that. I didn't capitalize the beginning of it, did I? What does this represent? Well, what does that represent? Well, absolute value makes it positive. So she's running away, she's running toward, but we're going to count it like away. She's running away, and this girl's running away. She ought not. But anyway, she's running, and we're going to total up the distance she ran, so all my negatives will count as positive. And so I just said total up the distance, but here goes. This is the total distance that Johanna jogs. Okay? All right. I almost did it again. Almost jumped to part C. We're not done with part B. Approximate that value using a right Riemann sum with 4 subintervals indicated in the table. Okay, well, let's back up. We're going to approximate this with the absolute value. So immediately, keep in mind that's going to be positive. And it's a right Riemann sum. So here goes. There's a rectangle. Goes from 0 to 12. What's the height of that rectangle? The one on the right. What's the height of this rectangle? 240. What's the height of this one? Positive 220. What's the height of this one? Positive 150. So here goes. When we approximate that using a right Riemann sum with 4 subintervals indicated in the table, then I'm going to say that this, the total distance that she traveled, is approximately, and here goes, my first rectangle is 12 wide and 200 high. My second rectangle is 8 wide, 240 high. My third rectangle is 4 wide and 220, positive, high. My last rectangle, and this is where my other mistake was, I was looking at these numbers and I was like, 8, 4, and it's easy to get into a mode of thinking that's just like, yeah, basic math, I got this. Just don't underthink either, I guess, is my suggestion. This is 16. I put 6, okay? I like 24 to 40. I mean, it's obvious, right? But we are sometimes doing such complicated math that we forget some of the other aspects of it. So we can do this, and we shall. So here goes. This is equal. I'm going to say equal. I mean, this is approximately that, but this is directly equal to this. This is 2,400 when you multiply those out. This is going to be 1920, and you can do that. And then this one, 4 times 22, well, that's 88. And 16 times 15 is 240, but we'll put an extra 0 there. And when we add all those, we're going to have 7,600 what? 7,600 what? Now, they didn't say use units, but let's do it because it's a good habit, and we do want to put this in the context of a problem. This is the total distance that Johanna jogs. Actually, I need to back up and add a little bit more to that sentence. This is meters. And I've realized a slight mistake I've made. Let me back up and say this. Back in the first sentence of part B, and when I worked this out originally, I did this, and I'm not clarifying it correctly. So we're going to correct this sentence right here. Using correct units, explain the meaning of that different integral in the context of the problem. And when I'm in the context of the problem, I really need to say what is truly going on, even with the units. So I'm going to add a little bit to this. So this is total distance that she jogs. That's actually not true. Well, first of all, total distance in meters. So sorry to make you add something to your sentence. But I don't know how far she jogged. Total. This is only the distance that she traveled from 0 to 40 in the first 40 minutes. Jogs, let's take that period out. Boom, gone. For 0 to 40 minutes. Okay? There we go. Put it in the context of a problem. I apologize that I did not do that. All right, let's go to part C. We're ready to move on. I didn't tell you how much those were a piece. Let me do that really quickly, then I'll move on. Okay, here goes. That is a point. The Wright-Riemann sum is a point, so there's one. And then this explanation, this entire sentence right here, is a point. And I am of the impression that they would probably count it wrong had I left off the units and the context of it from 0 to 40, because I can't just say that's how far she went. Well, maybe she kept on running after 40, right? All right, here goes. Part C. Bob is riding his bicycle along the same path. I wonder if Bob and Johanna know each other. Bob is riding his bicycle along the same path from 0 to 10. Bob's velocity is modeled by that, where t is measured in minutes and b of t is measured in meters per minute. Find Bob's acceleration. Acceleration is the derivative of velocity. They gave me velocity. Okay? So that's all we're going to do is find the derivative of that, plug in a 5. Okay? Now, let me tell you what not to do. Here's part C. Don't say A of t equals what? Don't be like A of t equals 3t squared. No, I need to really show them that I know that the acceleration is the derivative of velocity. And in this case, velocity is represented by the capital B because that's Bob's velocity. So here we go. It's 3t squared minus 12t plus 0. Okay? I want to know what happens at 5, so the acceleration at 5. I've already defined A as the derivative of B, so we're good to go from here on out. I can use the letter A as a function. So 5 squared minus 12 times 5. Let's see, that is 25 times 3 is 75 minus 60. So that's going to give me 15. 15 what? Well, let's put it in the context of a problem because they said so. That is meters per minute because it's acceleration, right? All right, we have done part D. By the way, the answer was a point, and using B prime is a point. So maybe I'd get the point here, maybe I'd get the point here, but either way, taking the derivative. All right, part D. Based on the model from Model B from part C, find Bob's average velocity during the interval from 0 to 10. What's average velocity? Okay, well, the average value of a function is represented by this. Let me use this random red piece of paper that's laying right here. So average value of a function is this, goes from A to B of my function. So this would tell me how high my function is, and then I would basically divide it by how wide it is, and that would tell me the average value. There's a whole lesson on this stuff. That lesson was called the second fundamental theorem of calculus, but this was attached to it. All right, here goes. The average velocity is that. So far, see, I want to know his average velocity from 0 to 10, and then the integral from 0 to 10 of Bob's velocity. So we'll just start working on that. Let's keep going. 1/10 of everything that's about to happen, whatever that is, 0 to 10. And let's see, let's find out what Bob was. Bob was t cubed minus 6t squared plus 300. And that is dt. 1 over 10. And we're going to integrate this. We have to do it by hand. We can't use a calculator. It's not going to be hard, though. Let's see. Antiderivative of t cubed would be 1/4 t to the 4. I'm going to call it t to the 4th over 4. Same thing, right? And then that's t cubed. 6 divided by 3 is 2, so minus 2 t cubed, because if I took the derivative here, I'd get that, plus 300t. And all this happens from 0 to 10. I'll plug in 10. I don't need to plug in 0, right? Because the 0 is going to vanish anyway. It would be, well, 0, 1/10. So 10 to the 4th over 4 minus 2, 10 to the 3rd, plus 300 times 10. And you can skip some steps here. I could have skipped some of that. So 1/10 of, okay, well, that's 10 to the 4th. Well, that's 10,000 divided by 4. That is 2,500. Don't get lost in the zeros here. That's 1,000 times 2, so minus 2,000. And that is 3,000. All right, pretty straightforward. That's 500 plus 300. That would be 3,500. You can already see what's going on here. And we have 350. 350 what? Average value of the function. What is the function? Well, the function is b. What does the function represent? Bob's velocity. How do we measure Bob's velocity? Bob's average velocity of the bicycle, meters per minute. Bob averaged 350 meters per minute in the first 10 minutes. Okay, here's a point. The integral was a point right here. The antiderivative was a point. And the answer was a point. What about that 1/10? Well, that'd have been wrong if you didn't have it back here anyway. All that stuff in the right place.